So what we want to look at is we want to get some tips and tricks. This is really, I want to underline the tips and tricks here. Perry's here for a reason, and we want to get that the most out of him and his knowledge. And the especially in porcelain fused to metal and PFMs. In the Sintron, it is a little bit different. There are a couple things different. He can tell you all about it. One I can immediately think of is the oxidation and the degassing, which is unnecessary, but he will tell you more about it. We'll have a look at the theoretical workflow a little bit, process overview, the advantages of using Sintron over any cast metal, the capabilities of the bridge split, and how it might actually now be no longer necessary because our N 2 came out and it's larger. And the reason for the bridge split was mainly to reduce the size so that we could sinter restoration in our overland. Some cam options, nesting tips and tricks, ceramic veneering tips and tricks. Okay, so to the theoretical workflow and process overview. Benefits of digital material are it is an easy CAD design. We can design the framework or substructure with the appropriate support for the ceramic by making full use of the cutback functionality, how it is in our Ceramill software, where you can have a specified amount of space from the full contour to the cutback restoration, leading into optimal support of your porcelain. Right? Nobody likes chipping, and I guess the most common cause is that the recommended parameters are not being kept. If you're somewhere in between a millimeter and 1.5 millimeter, I think you're good. Maybe Barry can say a couple more things to that. What his experience is.
Yeah. Richard, that's one of the things that was so exciting about this. You know, if you're waxing by hand and you know, you could do a wax up before you build the porcelain, and you could make a matrix on top. And so when you design your substructure, you can put the matrix on. That's a lot of work, you know, to do that. And
right.
So being able to design it on the computer, then do a cutback of 0.8 or, you know, whatever you're trying to achieve, and then all of a sudden, all your porcelain is shrinking equally.
Right.
Because it's all the same thickness everywhere. And it just makes it so much nicer when we do a buildup. And of course, we do a buildup where, you know, it's to full contour. And hopefully, we hardly have to do anything to it after, except maybe when we do the occlusion, we might bump in the wear facets or something like that. Mm-hmm. And so it allows us, because we're able to design it this way, it allows us to build the porcelain better, which saves us a lot of time. We don't grind in anatomy or contour and all that kind of stuff. We just bump the contacts, bump the occlusion a little bit, and it's ready to polish and go out the door. And so this has speeded us up tremendously. And so, you know, it's an easy CAD design. We're using teeth from a library or even our own library, or, you know, and then we're designing a substructure that enhances what we're trying to achieve with the porcelain. It makes it a lot easier.
Right. Yeah, I agree. I think that's awesome to hear that. What's in your opinion a good value? For me, usually it works to make in the software the cutback with 0.8, because by the time when I smoothen over everything, it sounds like not a lot, but once I smoothen over everything, I'm ending up being somewhere in between 1 and 1.2 millimeter, which for me is ideal.
Yeah.
Would you agree?
Yeah. Yeah. Sounds good. Yeah.
Okay. Now I've seen the number has changed now. I think in the latest software update, the defaults changed a little bit. So now it's a millimeter. So you're gaining a little bit more space. The thing where you're going to be careful is if you don't have a lot of space in the first place, and you're trying to make a cutback of a millimeter of what you think is the final space, what you want to have, and you forget about the smoothing of everything, that also takes some material off, then you might end up with not a lot of anatomical support. And it almost looks like an offset coping.
Yeah, and a lot of times you run into a problem, like if you have lower anteriors and you do like a millimeter cutback, half of it's gone at the incisal, so you can't
Right.
cut back as much on those. So
Right.
so you have some length there. So anyway,
that's right. All right, let's see what else we have. Minimize adjustment is perfect. The point didn't came even up on the presentation yet, but Perry was already talking about it and just confirming that. Repeatable quality, meaning not only your material is more predictable because it's industrially made and comes always out the same. If the steps are followed accordingly with the gas, etc. But also the design is predictable quality and repeatable. We're cost efficient. I haven't seen or made an updated version for the Algovan 2 because that is a little different size, different gas requirements, but it should be roughly the same, like we're used to. Easy redos if that really would be necessary, but yeah. And then all the other benefits of CAD/CAM, of course. And then, of course, I already mentioned that the benefits of an industrial manufactured product, where we can get the advantages of the sinterization and over the casting, where on a casting you're always going to have hot spots, cold spots in your muffle. Things are cooling down quicker than others, and the grain size and structure of the material is just not going to be as uniform as it can be with a sinter product or industrially made product. And we can get rid of all those issues with miscasts and etc. I've done a fair number of non-precious in the laboratory where I worked before joining Amanngirrbach, and I can tell you something about it. But maybe Perry has some insights on the industrial.
One of the things I did want to bring up, where you mentioned something about the composition of the alloy, and I dug in and really started looking at, okay, what is chrome, what is cobalt, what is molybdenum, what other trace elements are we using, and start looking at those alloys. And when you go back in history, 1970, gold was about $40 an ounce. In 1980, it was around $600 and something an ounce, and even hit around 800, 700 and something in that era. Well, when you look at what we started using for base metal alloys back then, base metal alloys really got a bad rap. There were a lot of us hated it because it was hard to work with. The alloy that we used the most was probably a nickel-based alloy, which most people used. The thing about it is, we've been using chrome or the chrome alloys we use today since 1939 intraorally. We also, when they first were developed, the Vitalium that we use for partial frame alloys is a cobalt chrome alloy. Well, the thing about it is, it was first developed for knee joints and used in the body, so it's extremely biocompatible. So the idea of, we don't want to use base metal alloys in the mouth, most of that can be blown away, especially if you take the individual metals that are in here. When you take the chrome, the cobalt, and all of those metals are necessary for the human body to function properly. As a matter of fact, all of these have to do with converting enzymes into usable vitamins in the body, like B12 is one of them. And also, what they found out was kind of interesting. When they first went into New Zealand, they turned the cows loose, they turned the sheep loose, they started walking around. Next thing they knew, hair was falling out on both. And they thought, what is going on? They had to supplement alloys to them because the ground didn't have enough in it. And what it was is they grazed, they breathed in just enough dust from the dirt that they got the trace elements of what they needed for their bodies to function properly. The way a cell operates, these alloys are needed in there. And that was just weird. I never knew all that stuff. So when you look at the alloy, matter of fact, the first mechanical heart had cobalt chrome in it, and it lasted for 30 years inside. The guy died 30 years later. So, you know, you look at the bad rap that base metals alloys have when you try to, you know, tell the doctor, say, doctor, I know you've been using noble, I know you've been using high noble, but let's forget about the bad rap that base metals had. Take a real look at this alloy. When you really look at the science and you look what's really there and you learn the truth, all of a sudden it doesn't even look like a base metal anymore. My dad has 2 knee replacements. Both of those are cobalt chrome. My coworker, Lisa, that works with us there in the lab, we've worked together for 30-something years. She has a hip replacement. Guess what it's made out of? Exactly. So I don't think there's a problem with using base metal alloys in the mouth as long as it's an alloy like Sintron, and those alloys are necessary for the body in the first place. And so I just thought that was kind of interesting when I dug into all of that, and it kind of did away with some of the bad rap that base metal alloys had, you know, from back in the 70s. So anyway, I just thought it was kind of interesting.
Interesting, yeah. I didn't know that. Yeah, that's crazy. Yeah, the R&D has, and I gotta apologize. This was maybe a little last minute change with the presentation. Otherwise, I know there's some great stuff from R&D available where they made actually some tests and showed great pictures about the uniformity of the products. I might have the one or the other in here, but I took some of the stuff out of this presentation because otherwise it would have been way too long. But basically it is more uniform than anything cast, just because your sintering and the process of the production is very different than from when you're casting it and potentially overheating it and changing the whole alloy. All those composition wise fine-tuned elements in there, they all go out the door if it's being overheated and treated differently than it should be, and it's difficult to judge that, I guess, with any way of casting, no matter induction or open flame. So looking at the process, there were fabrication wishes, and one of the wishes was to do that in-house using affordable compact milling machines. The mills have already been in the field, and there's plenty out there. And to eliminate non-precious metal casting process, basically for those reasons what we were talking about, no more wax milling, investing casting. Of course, it's always an option, but the sintered metal is just on a different quality level. The process was supposed to be reliable, cost-effective, and for the non-precious fabrication, and hopefully having a low tool wear with short milling times. And that was like the challenge basically with looking at the hard state metals. Yeah, you can do them, but the machine is going to cost you a fortune if it's going to be sturdy enough in order to cut the solid metals. And then your tool abrasion is going to be super high if you're going to cut that in a solid state. So the Sintron is perfect because for whoever out there doesn't know what it is, it's a wax-like hardness structure, and you can mill it really, really fast. Do I have some here? Yep, I have some here. I can actually show it. I dropped it, so something broke, so you can see how soft that is. I can actually probably break something here off from it. There it is. That's how soft it is. I can scratch it literally with my fingernail, so you can imagine how fast you can mill that stuff. And same wise, the tool abrasion is relatively low, and therefore you get a low cost. And then it shrinks. That also maybe gives you another idea. Shrinks about 11%. So from the material wishes, not only fabrication wishes, but the material wishes, high quality, homogeneous blank material, and reliable process with easy properties for veneering, porcelain, etc. So maybe let me pick up on that, because I've heard some questions quite a bunch, and maybe you can say something about that, Perry. I know a bunch of people ask me about how is the oxide looking? How is it? I mean, I can tell you something about it, and I probably have in my last webinar, but I would love to hear it from Perry, what kind of results he's getting, how he's doing it. Are you degassing? Are you skipping on it? I think I know the answer, but I would love to hear from you.
Yeah, we skip the degas altogether. We sandblast and steam clean, and then immediately apply opaque. Most chrome alloys, if you degas ahead of time, and I may not use the right terminology, but it's like the oxide, when it has a head start, tries to grow through the opaque. Now, some of the old chrome that we used that was milled from other companies way back that we were applying porcelain to, like for big bar cases and stuff like that, first thing we did was degas them. And then we'd put 3, 4, and 5 coats of opaque on, and it's like this black was trying to grow through. Well, then we realized that if we just put a coat on to start with, then it's like it stops the growth. And by the time you put the second coat of opaque, it's gone. And so that's when we started not degassing the chrome itself. And so again, all we do is sandblast 50 micron and steam it, and then immediately put the opaque on.
Okay. Did you say 50 micron?
Yeah, I usually do it with a 50 micron. Yeah.
Okay.
Luminous oxide.
Yeah, yeah. Maybe check and consult your porcelain manual. I feel like I know from a few cases, but using a specific porcelain which required, I think they said 80 or 100. And 150 is probably going to be too rough, in my opinion, because you're going to be careful when they're.
Yeah. One of the things that you look at if you look at the, we're all trying to achieve a superior bond strength. And so if you have one size etch, the microscopic pores it creates, and you have a grain size that's the same, those two actually match together better. It's like they interlock slightly. And it's the same way with composites. Depending on the company the composite's from, if you match the grain size or the particle size in the composite with the blasted surface and get it correct, it creates much more surface to actually bond. So it's not like it's a chemical bond, but it creates more surface, so it's stronger. And so it's the same way with porcelain. If you know the grain size of the opaque that you're applying, if it's a 50 micron grain and you've got 50 micron etched holes, those two lock together almost. And so depending on the grain size, if it's 70 or if it's 80 or if it's 150, those two matching create a better bond. And so you're right, that is something that could be looked at. Most of the time your bond strength with firing porcelain on there is great anyway. But if anything that we can do to help ourselves, it'll be better.
Yeah, and there some do require also a bonding agent in between. So it's usually a liquid, right, what you're applying. And there's on that specific porcelain what I have in mind, the ceramic is one thing, and then it got an updated name, and the bonding agent's actually from a different name, but it's all coming out of the same house. So it makes sense if you're looking at it then, and if you know it, but it's a little bit confusing at the first sight. So better to consult that, and it might be pretty small somewhere hidden in your instructions to help you. But usually that's the sandblasting, as the black oxide eventually, which you can prevent by just skipping on the oxidation altogether. And if you're consulting our manual from the Sintron, that's totally okay to do so. The one thing what you don't want to have is you don't want to have it coming black out of the sinter furnace, right? Because that basically would tell you something went wrong with your argon gas. Maybe the bottle was empty, maybe there was a leak somewhere of some sort. So it never had the chance to create that atmosphere which prevents oxidation. And once you open the augment chambering system and look at the finished sintered result, you should have like a silver to maybe with a little bit of red hue color, silver, golden, almost look to it. And then you can go straight on sandblasting, steam clean it, bonding agent if needed, and opaquer on it. And then you should be good. Save some time down the road too, not having to do gas.
Yeah.
Yeah, and so we had all those questions and things on the wish list on, hey, we would love to do this, and then there was Sintron, and there's comparable products out there meanwhile, but our RMD keeps a close look on them, and nothing really compares to the Sintron as of now. And it's not been too long ago that I spoke to our RMD team and verified that. And some of the reasons are it can be dry milled, has that soft wax-like consistency, which makes it very affordable to be processed. Dry milling, not everybody has a wet mill, etc. It can be processed in-house on a motion and micro machine type. Of course, there's different variances of it. There's a micro 4x, micro 5x, motion 1, 2, you name it, right? No more casting. There was initially a lot of pictures in there of all the reasons why we all want to get rid of the casting process, right? And this might be an additional material indication product what is going to help you to get a better amortization of your CAD/CAM system what you bought. If you're already doing zirconia, most likely that's probably the main reason you bought the CAD/CAM system for. Well, why not add another thing to it which is going to help you pay off that system? And process reliability. Some folks try to copy it, and I've heard some really interesting and fun statements from customers telling me what the competition told them. One was, for example, we now see the Amanngirrbach furnace here. Oh, here's our product, but you should use the Ceramill Amanngirrbach. And I guess the reason is that there's patent on that augment sinter box, and it just cannot be copied straightforward. And the other sinter furnaces which are out there, they are then, because they are missing that crucial part of the augment, they're having a much higher consumption of sintron, of argon gas, and that's going to bring your cost up. Maybe your sinter results are not going to be coming out consistent, so maybe you're having some parts which have been partially oxidized. Yeah, also the quality of the material is not quite on par. People tried, it looks like, but couldn't quite get to it. So Ondi took other materials and sintered it in our furnace with our requirements, with our shielding gas and everything, and it still wasn't quite the quality what the Sintron is. And I'm trying to scratch my head over when we came out with it. It's not since yesterday, so it's pretty established product meanwhile. It's just unfortunately a little bit forgotten, so you're trying to revamp it a little bit. And part of that is too, let me go back, you see in the middle is the first generation augment, and on the right hand side in the furnaces you see actually the augment 2. We will get to the augment 2 and what has changed. You have more space now basically to cut it short, but also it's no longer a wear item. So the Sintron comes in 71, 98 shape. We have 6 different heights ranging from 10 to 12, 10 through 12, 14, 16, 18, 20, 25, I think. And then I already mentioned that approximately 11%. That depends on the blank, same story like with zirconia. It's developed specifically to be processed with the Ceramill system, but now others can also do that. So I know in the beginning some of the roller mills had some issues milling it, but meanwhile I think had to do with the exposed rail, but Roland made some changes to it, and I think they have it officially listed meanwhile. We're looking at about 25 to 30 units out of a 71 blank, and that of course is because it's usually a cutback, so it's a little smaller, right? milling time is approximately 10 minutes. That's a very average number because it really depends on which kind of strategy you're picking. You have such a vast choice what you can do now. Standard, fine, HD, margin standard, margin HD, undercut standard or HD. So yeah, that can go somewhere from 10 to maybe up to 25, maybe, who knows. So here you see the first generation augment. We were able to hold approximately 30 units in it. And the sinter ball and possibly the sinter hood needed replacement after about 20 sinter cycles, more or less, depending on how well you took care of it. And now we have the augment 2, where you see immediately the size has changed, and all of those are no longer considered wear items. So the first generation was a cast metal. This is a very different material here, and the way how it's made, and the tolerances have increased as well. So if really something would break, then in the first generation it was only possible to replace certain parts by themselves, and if, let's say, something happened to the sinter hood, to the very large lid on top, then you had to replace the entire base plus the hood because it fit together perfectly. So you had to actually get a whole new auger vent. Now that's no longer the case. You can replace every single thing. It has a weight on top just because it's more lightweight, and it needs a updated program because the auger pressure is different, etc. So there's on our website in the C3 portal, you can log in, download the update for it, make sure you're picking the right furnace because there's an update available for the Augotherm 1 for the more boxy version, and the Augotherm 2, what you're seeing on the screen here. And you have to download the correct one, install it on the thumb drive, plug the thumb drive into the furnace, turn on the furnace, and it's going to beep, and it's going to tell you that it's ready, and you can save it right from there. Same thing. The minimal auger consumption is still a point here. Even though we're increasing the pressure, we are also now getting more units into the sinter tray. And I think the labs can organize it in a way that the tray is maximized. Of course, if you were now always sinter 5 units in it, comparing the old version to the new version, now you have slightly higher auger consumption. But if you can compensate with the larger size, I think you're good. We're talking about approximately 25% more capacity, up to 40 units now versus the first generation of 30 units. The better handling through the new shape, and the biggest thing is not the amount of units for me, it's the size, because not all full arch cases are fitting into the Augment 1, and some needed the bridge split option where in the CAD software would basically separate it into 2 pieces and then solder or laser weld or whatever at the end. It can be used with existing equipment. I already said that. So the first generation Augotherm still can get that. It comes with appropriate instructions because things have changed. The powder, what's mixed into the beads, and separately available. The amount has changed. So if you were one of those refurbishing the beads, basically, if something would have happened, and then weighing out your own powder, the amount was 2 grams. Now it's 2.5 grams. And the amount of beads has changed from 100 to 150 grams, I want to say. But don't take my word for it. Consult those instructions. You see the YouTube link there. I'm not going to go there right now just because we are already 34 minutes into the webinar. It was supposed to be a 45-minute webinar. So go to YouTube. You'll find those instructions. Yep, here you see that. The gas pressure has changed. Without sinter pearls, you can also do that with the float sinter disc, etc. There's an instruction video on it, same thing. And here maybe some of the results. So this is about the size, what you could do from, you see that here, that is the blue hue of that cast metal. It changes the color eventually. This is pretty much how it should come out. So here you see the color of the material. It polishes really well. We have a couple more pictures in from Perry as well. Just to summarize a couple of those features again. So basically, it all links together. It's not just Sintron. It's the Sintron material together with a good CAD/CAM system, together with a good furnace with the correct program on it, proper milling strategies, right? The sinter box, which not everybody has, the augment, now in the second generation, and in between there were a couple updates like the augment evolution. And you see the finished units of the run. Maybe Perry can talk about his experiences with long bridges, warping, stabilizers.
Well, one of the things we did, and I noticed that in some of the photos you've done also the same thing with some of those cases, is where anything that looked like it was just a really huge mass, like if you notice some of the ponics have been drilled through, that the hole has been drilled in. And then also the stabilizer was reduced a little bit. And so we've been doing some of the same things in that way. But even in zirconia, we have run into that, where you have a really large ponic and you fire the porcelain, and the porcelain on that really large ponic doesn't mature quite as well as the rest of the porcelain on it. So that's any material you use. If you have a large mass and then you have a thin abutment, it does create some differences there. So with the Sintron, it's the same way. We've reduced some of that size. You remember early, that stabilizer was huge, and it was like this huge mass, and sometimes I felt like it was maybe shrinking more than what the actual bridge was itself. So you know, that's one of the main things that we did. The other thing that we did that you know, there's a certain amount of connectors there, and I remember early on, I think you even helped me with this early, I was always having too many connectors. It doesn't take that many, and it seems like we actually got a better result by having fewer connectors. And so that was another thing there. And then we also watched very carefully about the way we handled it. I remember one case that we did, I actually dropped it at the bench, and I looked at it, and everything looked great. But then when we put it in the mill, and we started working with it, we realized it had had a crack in it at some point. And so the way you handle it and the way you touch it and what you do is very, very important. The other thing is when we actually go to the mill and mill, which for us, we have 3 AG mills. One of them is dedicated specifically for Sintron, and we don't mill anything else in it. And one of the main reasons we did that was because the material itself is a little more contaminant, you know, as far as getting on other materials. But it just made it easy for us to, you know, any little flake of something thick in the wrong place and get your burr off just a hair created a problem. And so to me, for us to get everything to fit perfectly on these big cases, we had to be meticulously keeping everything clean, and we had to make sure that we use the my mind went blank, what do you call it? Not update, calibrate, I'm sorry, to make sure everything was calibrated, you know, 100% all the time. And once we started doing that and really keeping everything clean and watched the way we handled it, everything started falling into place a lot better. So
that's great information there. I'm glad you said that with the stabilizer connectors. Yeah, absolutely. I think everybody made a couple of mistakes in the beginning. I for sure made my stabilizers as well too big in the beginning. Probably had too many connectors going on. Talking to other technicians just helps a lot. Alex probably would confirm that. I know, I mean, talking about Alex Winche, I know he confirmed that for me for zirconia cases for sure, because that was the recommendation, our official recommendation from Amanngirrbach, stabilizer, and the size might actually still be beneficial if you can extend it to the posterior, because then you can still make a T-ball stabilizer. I can stand it up maybe in a zirconia.
Yeah.
Sintron furnace, it doesn't even work that way, because you wouldn't be able to stand it up anyway, so it doesn't matter. In zirconia, if you do that, if they extend it, make a T-bar out of it by taking this to it and cut through it, at least maybe reduce the number of connectors. That even though you have a long stabilizer, that's not really too many connectors going on. And make sure they're straight. If they're all looking in different directions, then that's going to pull into those directions. If they're all uniform, spread out, then you're getting a better result. Yeah, I'm glad you're confirming that. That's great.
Yeah.
So I didn't want it to really say names associated with porcelain or something associated with issues, which we had earlier. But since you had many successful cases, do you want to tell us which porcelain you are using on the Sintron?
Well, we've used Design from Ivoclar. I have used Omega 900 from Vita. I use Creation CC. And I've also used a little bit of the old Ceramill Plus, Ceramill Plus porcelain. And so we have those 4 porcelains in the lab, and sometimes I'll just grab one and use it. Sometimes for maybe I might even be out of a shade on another one and grab that, or something like that. But all 4 of those have worked great, and we've used them even on bigger cases, smaller cases, all that kind of stuff. So and we've never had any issues with any cracking or anything. I know I took a troubleshoot call one time. A lab, they were using the Sintron, and they were using, like you say, you don't want to mention names or anything, but they were using a really old school porcelain. And it even surprised me that somebody was still using it. I was just kind of like, you're kidding, but anyway, they were using that, and they were getting some cracking, especially on Ponix, which, to my mind, I thought, well, yeah, that's where the issue is, where, and of course I suggested to them to hollow the Ponix and make them smaller, so that the heat is a little bit different there. And they never did come back to me and say, yes, it worked or didn't work or whatever, but I wanted to tell them to change porcelains, but you can't do that. So anyway, this is one of the last cases, the Sintron. Now this isn't a full arch. If you'll notice, 8 and 9, the 2 centrals are splinted, and then we have from the lateral back on each side. The biggest thing is, look at how uniform the entire arch is, and then layering porcelain on this, everything's going to shrink exactly the same. Now on this one, the Ponix are it looks like they're really big, but they're not that tall. And so, we have it, we didn't have any problems with porcelain firing. There was no warpage here, and we didn't have any issues like that. So that worked out really well on this case. And then too, the only other thing that I would do sometimes, because the porcelain is a little bit thinner, sometimes I go ahead and set up my mamelons in the alloy, which just helps me in doing the porcelain and keeps me kind of stay on track a little bit. I didn't do it on this case here in the photo, and I don't even think I did it later, but I wanted to go ahead and get a photo of it while I had it done. But I hardly did any metal finishing on this at all. I just barely went over it. I call myself getting the oxide layer off, but there's no oxide layer, so it's not anything to worry about there. So, this is just works. And so, this is the main photo that I wanted to show.
Those pins, are those residue from the stabilizer, or did you design them to grab the restoration that you can easier stack the porcelain on it in the CAD software, or is that like a connector what you left over from the milling to hold on to them?
Let me get some things off. You're talking about on the connector part. What we did was we always place a connector that we leave a certain length so that we can clamp it with hemostats.
Yeah.
So that it's easier to apply, whether it's opaque or porcelain or glaze or whatever. We just always leave a little piece on there to be able to hold something. But that's what that is.
That's why I thought. I just wanted to get your confirmation on it. So because in the early beginning, people have been, including myself, have been trying to design a little thing on it, what you could grab with the hemostat. But if you actually nest this then in the CAM software, it bulks it out because it somehow has to mill it. So you're ending up wasting material. It's better if you're just making it without it. Maybe make a little collar or something if you want in the design. Yeah. And then in the nesting, to reduce the diameter of one of the connectors and just leave it on there. You can even have the mill cut it off with 100%, even if it's very thin, because then that won't fall off if the mill cuts through. And sintro just with it, and you have something to grab it.
Yeah, that's what we did. We just leave one of the connectors on there, and don't cut it off 50% or anything like that. So,
well, guys, I hope that was helpful. Perry, good to see you again. I hope I see you soon.
Yeah, good to see you.